Let's take a look at this dynamics unit test now. Question number 1. 1,500 kilogram car is traveling at 25 meters per second on a level road when it runs out of gas. What's the force of friction if it takes 45 seconds for the car to come to a complete stop? We know this is a group B problem. It involves acceleration. So let's keep that in mind. Write down our givens here. 1.50 times 10 to the 3 kilograms is our mass. We've got a velocity here of 25 meters per second, and that would be the initial or the final. That would be the initial velocity. It's the speed that it's going before it runs out of gas. Runs out of gas, it's going to stop. So we're going to say VF is equal to 0 meters per second. What's the force of friction if it takes 45 seconds is my time interval here. And we're looking for that force of friction. Now, we know we're allowed to try this equation. This is a valid equation. F is equal to mu times the normal force to find the force of friction. That doesn't look like it's going to be helpful to me, though, given what I have given to me in the question. So let's try something else. In the end here, we know that as this car is coming to a complete stop, there's one force that provides the net force. The net force is equal to m times a. If there's one force that provides that net force, that force of friction is the net force. So let's say F is equal to m times a, but I don't know what the acceleration is. So I have to find that as well. Let's say A is equal to delta V over delta T. We're allowed to use any of those group B equations here, although this one looks like it's the one that's going to fit. 0, the final velocity, minus the initial velocity of 25 meters per second, gives me an acceleration of negative 0.55556 meters per second squared. Now we find that force of friction, or the net force, which is the force of friction. We're going to say 1,500 kilograms, that's my mass, times the acceleration that I just found, negative 0.55556. That gives me a value of negative, the 2 digits, negative 8.3 times 10 to the 2 newtons. And that negative should make some sense, right? If we're moving forward, car is going forward, that force of friction that's required to stop it is going to be backwards. It's a negative force. Question 2. Warren and Jaden are pulling a rock of mass 100 kilograms across the ice. It's a frictionless surface, or at least we're going to say it's a frictionless surface. Warren pulls 150 newtons at 30 degrees north of east. Jaden pulls 120 directly south. What's the acceleration? The acceleration of the rock. Not looking for the net force here, we're looking for the acceleration. But we got to get the net force first. So let's do that. Let's draw this out here. Warren is pulling with a force of 150 newtons at an angle of 30 degrees north of east. We're just going to call Warren's force F1. And then Jaden is pulling directly south. That's with a force of 120 newtons. We're going to call that F2. What do you see here? What stands out at you? Yeah, we've got a funny angle, and I don't like funny angles. So we take it off to the side, and just like we have a million times before, we get rid of it. Let's break this into our X component and our Y component. Do a little trigonometry here. The X component is the adjacent side of the triangle, so we're going to use the cosine function to find that adjacent side. Cosine 30 degrees is equal to X over 150. X is going to be equal to 150 cosine 30, which gives me 129.9038 newtons. And the Y component, we're going to use the sine function. Sine 30 degrees is equal to Y over 150, and that's the easy one to do in our calculators. We're just going to say that's 75 newtons. We box this off because that's what we do. And then we replace the X and Y components with 129.9038, and then the Y component with 75 newtons. If we had a pen, we might have to scratch this out. I can erase it, so I'll do that. Just to completely erase that 150 newtons forever. We're never going to use that again. Okay, now we've got to break this into our X and our Y components and add those X and Y components off. The X component of the first one, 129.9038. The Y component of the first one is 75 newtons. Both of them positive, right and up. The X component of the second one is 0 newtons because it's 120 newtons straight down. The Y component is negative 120 newtons, again, because it's down. We add these up, 129.9038 newtons, and these ones gives me negative 45 newtons. And then we got to just redraw that triangle now. Let's get a right angle triangle. That's the goal, right? Get a right angle triangle. So we get 129.9038, and then the Y component is 45 down, negative 45 or 45 down. And the resultant vector, this is the force that we're looking for here. And the net force, we're going to say that force, the magnitude of that force at least, is the square root of 129 squared plus 45 squared. That gives me a value of 137.4773 newtons. Theta is the inverse tan function of opposite over adjacent, 45 over 129.9038. And that gives me an angle of 19.1 degrees south of east. But what are we asked to find here? Not the net force, but the acceleration. So let's say A is equal to F over M. 137.4773 newtons divided by the mass. Mass was 100 kilograms. That's going to give me an acceleration of 1.37 meters to 3 digits, that is, 1.37 meters per second squared. And our angle is going to be the same as the direction of the force was, 19.1 degrees south of east. So final answer, 1.37 meters per second squared, 19.1 degrees south of east. If you forgot to find the acceleration, you found the net force, but you did it correctly, you would have lost 1 point on this one. You got to read that question carefully, right? We're asked to find the acceleration, read the question, answer the question. Question number 3. The coefficient of static friction between plastic and concrete is 0.50. Kinetic friction is 0.40. What's the force of friction that's acting on a 10 kilogram plastic box as it's being pulled on concrete if the force applied on the box is 35 newtons, 70 newtons, and 105 newtons? Does it move? We got to know whether it moves or not to find the force of friction because we don't even know what type we have until we know whether it moves or not. Well, there's nothing in this question that tells us whether it moves or not, so we've got to figure that out ourselves. We're going to do that by finding the max force of static friction. FSF max is equal to mu times the normal force. Mu is 0.50. This is the coefficient of static friction, 0.50. And the normal force on this case, presuming it's a flat horizontal surface, is going to just be the mass times 9.81. So we're going to say 10 times 9.81 here. For that normal force, we do our math there, works out to be 49.05 newtons. So this is the max force of static friction. If I push with 35 newtons, does it move? No. No, it doesn't move. So the friction will be static friction, and that value of static friction will simply be the value of the force that I apply. It's going to be 35 newtons. B, push with 70 newtons. Does it move? It does. The max force of the max force of static friction is 49. I got to apply a force bigger than 49 to get it moving. When I apply a force of 70, it moves. So let's find that force of kinetic friction now that it's moving. This is going to be 0.40 times the normal force, which is going to be 100 times 9.81. Calculate that value to 2 digits, it gives me 39 newtons. That's the force of kinetic friction. And in question C, I apply a force of 105. Yeah, it's going to move. That's bigger than 49.05 newtons. And that force of kinetic friction, remember, that's not the stubborn force of friction. Once we get kinetic friction, It is what it is. If it was 39 newtons when we push with 70, it's going to be 39 newtons when we push with 105. Anytime it moves, it's going to be a force of 39 newton kinetic friction. Four. This is a tricky question, actually. 4 says, suppose your friend wants a piece of candy from the 10-kilogram box she gave you. She then pulls the box by an attached string. The magnitude of the force exerted by your friend is 40 newtons at an angle of 30 degrees, but the box moves parallel to the surface of the table. There's a coefficient of kinetic friction of 0.125. What's the acceleration of the box? Let's draw this out. Here's the box on our surface. We're pulling it with a force of 40 newtons. I'm going to call that F1, 40.0 newtons. We get an angle of 30 degrees, like we often see. And we've got a force of friction that's going to act backwards here. We don't know what that value is yet. We have a force of gravity acting down. And we have a normal force acting up. But a normal force, it's not going to cancel gravity because we have that y component of the applied force that's helping the normal force counter gravity. We know that the downward force of gravity has to be equal in magnitude to the total upward force, but that upward force is provided by the normal force and the y component of that 40 Newton applied force. All right, let's deal with that funny angle. We have that funny angle. Let's take it off to the side, and let's get rid of it here, okay? We have 40 newtons right here. We have 30 degrees right here. And we have the x component, and we have the y component. We're going to have to find both of those, of course. The x component is the adjacent side again. So let's say cosine 30 degrees is equal to the adjacent side over the hypotenuse. X is equal to 34.6410 newtons. And the y component, sine 30 degrees, is equal to the y component over 40. So the y component is just equal to 20 newtons, half of 40. Box that off because it's what we do. And then let's replace this 40 Newton applied force with our x component of 34.6410 and our y component of 20 newtons. Now comes the tricky part. We have to find that force of friction. That force of friction is equal to mu times the normal force. But the normal force isn't m times g this time, because that normal force is helped along by the y component of the applied force. So let's say the force of gravity acting down, which is 10 times 9.81, that force of gravity acting down is equal to the normal force acting up plus the y component of that applied force acting up. So the total downward force is equal to the total upward force. When we rearrange this to solve for the normal force, we end up getting 78.1 newtons. So the force of friction is going to be the coefficient of friction, which is 0.125 times 78.1 rather than what a lot of people will put for this, which is 98.1. 98.1 would be the force of friction, the normal force, if there was no upward applied force. But since there is, we have to add those two upward forces to give me the total downward force. All right, we calculate 0.125 times 78.1. We get a force of friction of 9.7625 newtons. And now we can do our thing that we've done a million times before. The net force is equal to the sum of the forces, FF plus FX. We're not worrying about these anymore because all three of those combined have canceled out. The net force is also equal to M times A. M is 10 kilograms. A is negative 9.7625 newtons because it's acting to the left. And then the X component of the applied force is 34.6410 newtons. Now those numbers on the right side up, divide by 10 to get the acceleration, and I get 2.49 meters per second squared. I believe those of you who made the normal force just m times g, or 98.1, I believe you get 2.24 meters per second squared. You would have lost 1 point if you did that. Question number 5. What's the acceleration of this box? There's a force of friction acting of 20 newtons. Hey, which way is that friction going to act? If the mass A is bigger than the force of friction, it's going to move to the left. That means the force of friction is going to act to the right. Okay. So let's identify each of these forces. I'm going to call this FA, since that's what it's labeled as object A. That's going to be 10 times 9.81, or 98.1 newtons. FC, it's a little bit smaller. In fact, it's half the size because it's half the mass. FC is 5 times 9.81. And that's going to give me 49.05 newtons. Now, some of you like to straighten this out. That's okay. You can do that. That's great, in fact. I'm not going to here. I'm just going to say the net force is equal to the sum of the forces. That's FA plus FF plus FC. MA is equal to FA plus FF plus FC. And now we sub in our numbers. The mass is the total mass because the entire system is being accelerated. So we're going to say 20 times A. Now, this is where there is some value sometimes in straightening it out. That allows us to see that FA and FC, even though they're both downward, they oppose each other. So one of them's got to be negative and one of them's got to be positive. I'm going to make FA negative 98.1 newtons. The force of friction will therefore be positive 20 newtons because it's acting opposite to the applied force FA, but it's acting in the same direction as FC, 49.05 newtons. So both of those are going to be positive. They're both acting to the right-ish, and FA is going to be negative because it's acting in the opposite direction. We add those numbers up on the right-hand side. We divide by 20 kilograms, and we're going to get an acceleration of negative 1.5 meters per second squared. Question 6. 75 kilogram skier, including the skis and the poles. The diagram, has just begun descending a 30-degree slope. The force of friction between the skis and the snow is 65 newtons. So let's draw a diagram here. Let's draw a picture. You don't have to draw a skier. You can draw a box if you want. Whatever. Skier's going down the hill. Say a 30-degree incline like we usually see. We're going to say, what do we got here? We got a normal force, a force of gravity acting down. We've got a normal force acting perpendicular. We're going to switch the color of that though. A normal force acting perpendicular to the surface. And then we get that F parallel that's pulling that skier down the hill, right? You got to go down the hill somehow. Well, gravity pulls you down the hill, but if it was just gravity, you'd go straight down. It's gravity and the normal force combined that give me F parallel that actually is the force that pulls me down the hill. Now I'm going to label that F parallel up there. You know there's not two values of F parallel. It's only one force parallel, but we're just going to label it in two places. We're going to find the value of it down here, and we're going to use the value of it up here. Now we also have a force of friction applied. That force of friction is going to act in the opposite direction to the force down the hill. It's going to move down the hill. Friction is going to act up the hill. All right, now we got to find that F parallel. So let's go off to the side and do that. Let's say sine 30 degrees is equal to F parallel. That's the opposite side of the triangle divided by that force of gravity, Fg. F parallel is equal to mg sine 30, or we're going to say The mass here is 75 kilograms times 9.81 times sin 30. And that gives me a value of 367.875 newtons. Let's label that over here, 367.875 newtons. And we have that force of friction, of course, acting at 65 newtons up the hill. My F parallel should be drawn quite a bit longer than FF, but we're not going to lose any sleep over how long we draw those vectors. Should be longer because the force is a lot bigger, right? All right, now we're going to say F net is equal to the sum of the forces, F parallel plus FF. Why are we not including Fn and Fg? We are including Fn and Fg. When we calculate F parallel, that already is including Fn and Fg. It's the sum, the vector sum that is, of the normal force and the force of gravity. All right, the net force is also equal to m times a. The mass here is 75 kilograms times the acceleration, which is what we're trying to find here. The F parallel is negative 367. We're going to make that negative because it's acting down the hill. Now, some of you like to make the bigger force positive and the smaller force negative. That's okay. If you made F parallel positive 367, that's fine, as long as you make FF, the force of friction, negative 65 newtons. We add those numbers up on the right-hand side, divide by 75 kilograms, we're going to get negative 4.04 meters per second squared. And B says, assuming that she starts from rest, what's the velocity that she will reach after 4 seconds? We're just going to use A is equal to delta V over delta T for this one. Rearrange this. Delta V is equal to A times T. Now, technically, this is going to get me delta V, not VF. But if VI is 0, she starts at rest, then delta V, the change in velocity, is exactly the same as the final velocity. So let's say A is negative 4.04. Should be using my unrounded number here. But it does work out to be the same in this case. We multiply that by 4, we get a value of negative 16.2 meters per second squared. If you had made the F parallel positive 367 and FF negative, you would have gotten an acceleration of positive 4.04, and then you would have gotten a delta V of positive 16.2 meters per second squared, which would make sense, right? If you're calculating the final velocity, you should get a velocity that's down the hill. And if you made that 367 a positive value, then you defined down the hill as positive. We should get positive 16.2. The way that I defined it, though, I should get negative because negative is down the hill. Question 7. Nick pushes a 41-kilogram wheelbarrow from rest to a speed of 3 meters per second to a distance of 8 meters, assuming there's no friction acting between the ground and the wheelbarrow, and then Nick is pushing the wheelbarrow in the same direction it moves. How much work is done by Nick on the wheelbarrow? Let's write down some givens for this. Let's say the mass of the wheelbarrow is 41 kilograms. Let's say the initial velocity, the initial speed here is 0 meters per second because it starts at rest. And the final speed would be 3.0 meters per second. We're pushing that through a distance or a displacement of 8.0 meters. We're looking for the work done on the wheelbarrow. Now, we know we're allowed to do F times D, or F times D times cosine theta. Usually that ends up reducing to F times D. I don't think that's going to be helpful to me this time, though. I don't know what F is. So I'm going to say W is equal to delta E, the work energy theorem. That's the final energy minus the initial energy. Now, the final energy of this wheelbarrow is kinetic because it's moving. So we're going to say the final 1/2 mvf squared minus the initial energy. As the wheelbarrow is at rest, it has 0 initial energy. I'm just going to say 1/2 of the mass, which is 41 kilograms times the speed squared. Don't forget to square that speed. Minus 0 gives me 1.8 times 10 to the 2 joules. Now, some of you would have done this. Some of you would have actually went with the F times D. Theta would be 0, so cos theta is 1. The equation reduces to F times D. We don't know what F is, but some of you would have said, well, I'm going to find F. And how do we find F? By saying F is equal to M times A. Well, we don't know what A is. Well, I'm going to find A. So we could say maybe VF squared is equal to VI squared plus 2AD. Rearrange to solve for A, get the value of A. I didn't do it that way, so I'm not sure what the value was, but you could have. Subbed it into here to get the force, and then sub the force into there with the displacement of the 8 meters. And lo and behold, if you do it that way, you will get 1.8 times 10 to the 2 newtons. Go figure. You have to get the same answer if you do two separate legitimate ways. Now, if you got time, I'm not going to do this both ways to check my work as I'm writing the test. But if I finish the test early and I've got lots of time, maybe I do take a look at doing it the second way. If I get the same answer both ways in a question like this, I'm guaranteed that I've got the right answer. Question 8. A 100-kilogram go-kart, including the driver, is traveling at 7 meters per second on the top of a 20-meter high hill. The go-kart and driver coast down the frictionless hill. What is the speed of the go-kart and the driver when they reach the bottom of the hill? I'm going to draw this out. I don't really have to, but I'm going to do that. We're going to say the mass of this is 100 kilograms, and the initial speed is 7.0 meters per second. The height of the hill is 20 meters. We're looking for the speed down here at the bottom of the hill. A question like this sometimes is just a little bit easier to visualize if I have the diagram drawn. All right, we know that the energy at the top is equal to the energy at the bottom by the law of conservation of energy. The energy we have at the top is due to kinetic energy because it's moving, 1/2 mvi squared plus, we also have potential energy because there's a height. Now, when we get to the bottom, there is no height anymore, but it is moving. It's going to be moving faster, in fact. So all of the energy is just kinetic energy now. We can cancel those masses. You don't have to. You can use that 100 kilograms, sub it in. Makes the math a little bit easier, though, if we do cancel it. We're going to say 1/2 here of 7 squared. That's my initial speed squared plus 9.81. We make this positive, right? Because potential energy is a scalar. We don't put the negative in front of the 9.81 in that case. HI is going to be 20 meters, 1/2 of VF squared. We calculate that left side, this plus this, we get 220.7 equals 1/2 V squared. We take the half over by dividing by 0.5, or we can take the half over by multiplying by 2. Either way you look at it, you're going to get 441.4, and then we're going to square root that. And when we square root that, we get our final answer. 2 digits, because of the 7.0 meters per second, 2 digits of 21 meters per second. Now let's take a look at our multiple choice questions. Number 1, when the net force acting on an object is cut in half, the acceleration will, now if we take a look at the equation, A is equal to F over m, Newton's second law. If we cut the force in half, it's a linear relationship with the acceleration, so it's going to become half of what it was as well. 2, at a height of 1.0 meter above the ground, you hold a textbook with a weight of 8 newtons. That weight, remember, is defined as the force of gravity. If you're holding it still, it's not moving, then we're in a state of equilibrium. Here's the book. If we're in a state of equilibrium, then forces must balance. My force of gravity acting down would be the same as the applied force acting up. If those two forces are equal to each other, the net force acting on the text would be 0 newtons. The applied force would be 8 because it has to oppose the force of gravity, but the net force would be 0. Right? If something's at rest, it wants to stay at rest until an unbalanced force acts on it. If it remains at rest, then the unbalanced force must be 0. All right, 3 says a car is traveling down the road at a constant velocity. The net force required to keep it moving at a constant velocity. Once again, at a constant velocity, we're also in a state of equilibrium, although this would be translational equilibrium. Net force is 0, so therefore the force required to keep it moving would be equal to the force applied on the car to get it moving. Sorry, it would be equal to 0. The net force required to keep the car moving would be equal to 0 newtons. There's a force applied, and then there's force of friction probably acting backwards, maybe air resistance acting backwards, but the total force has to be 0 as long as we're in a state of equilibrium. Static equilibrium, translational equilibrium, doesn't matter. The net force is always going to be 0 there. A is our answer. 4. Alicio and Luke perform an experiment with a shopping cart at Safeway. Alicio pushes the cart with a constant force of 50 newtons while Luke puts soup cans in the shopping cart one at a time while he measures the acceleration of the shopping cart. Which of the following statements about the motion of the shopping cart is true? Acceleration of the shopping cart will increase. Now, you put more soup cans in there, it's going to get heavier. We're not going to make the acceleration increase. That doesn't make any sense. The shopping cart will continue to move at the same speed because the applied force remains the same. That kind of sounds a little bit like we were talking about in the last two questions, but not quite, because we're changing the system. We're making the system heavier, and by making the system heavier, we have to apply more force in order to keep it going at the same speed. The acceleration will decrease because of increased mass. That sounds about right? If A is equal to F over M, and you make the mass bigger, then it looks like you're going to make the acceleration smaller. That looks right, but let's just double check D, just to make sure. Your shopping cart will stop because the soup cans will apply an opposite reaction force. No, that would be Newton's third law, but that wouldn't apply here. Question 5 says the resulting motion of the shopping cart can be explained by, well, we said that A was equal to F over M. That helped us to see that the bigger the mass gave me the smaller the acceleration. That's Newton's second law, B. 6, Ambrose is riding in an elevator to the top of the Calgary Tower. While standing at rest on the ground, his weight or his force of gravity is 700 newtons. Which of the following situations would he feel heavier? In other words, which situation would his normal force be bigger than 700 newtons, be bigger than his force of gravity acting down? His normal force would be bigger when he's accelerating upward toward the top of the tower. Question 7. Mosquito traveling north at 50 kilometers per hour collides with a car traveling south at 50 kilometers per hour. The bug is instantly splattered on the windshield of the car. Which of the following statements is true? We know when object A, which is our bug here, applies a force on object B, we know that object B will always apply an equal and opposite force on object A. So the force on the bug is going to be equal in magnitude to the force on the car. The bug splatters, the windshield doesn't break. That has nothing to do with the forces being not equal to each other. That just means that the bug isn't as strong as the windshield. The bug applies the force of the windshield applies the same force on the bug. That force is enough to splatter the bug, but it's not enough to break a windshield. 9. A large crate is moving at a constant velocity. Two forces act, an applied force and friction. Which of the following statements is correct? The applied force is larger than friction. No, that's not the case, because we know that the net force, when we're in a state of equilibrium, the net force has to be 0. So that applied force can't be bigger or smaller. The applied force equal in magnitude, opposite in direction. That looks like it works for us. Let's just double check D. The applied force is equal in magnitude and in the same direction. No, if it was in the same direction, it would accelerate. Pauline, Emily, and Reese are each told to move a heavy block to a specified height. Pauline pulls the block up a ramp to a specified height. Emily pushes it up to the same height. Reese lifts the block directly straight up to the specified height. Which of the following statements is correct about the work done? Pauline and Emily do the same amount of work. Reese does less. Reese does more. different amounts. Now, they all do the same amount of work, right? They're all getting to the same height. Regardless of how they accomplish that, it required the same amount of energy to do that. So we'd say that the work done would be the same. 11 says, which concept or principle best explains why the cab of a truck is often separated from the load by a steel barrier? You know that when a truck has a lot of inertia, right? When it stops, that load of the truck, which is going to be usually pretty heavy, wants to keep going in a straight line. If it's not fastened down properly, then maybe it does keep going in a straight line. Sometimes you get this little steel barrier here to prevent this load from hitting the cab if the load keeps going in a straight line when the truck itself stops. So what concept or principle best explains what we just said? Yeah, that would be Newton's first law that says an object in motion, that would be the load, keeps going in a straight line at a constant speed until acted upon by an unbalanced force. That unbalanced force, if the load isn't fastened down properly, that unbalanced force that would stop the load from taking out the cab would be the steel barrier. 12, which of the following are scalar quantities? That would be kinetic and potential energy. Acceleration is a vector, force is a vector. So kinetic and potential energy, all types of energy are scalar quantities. And finally, question 13. On a playground swing, Avery reaches the same height with each consecutive cycle. Which of the following graphs represents the total energy of the swing as it moves back and forth? We know that the potential and the kinetic energy are going to change. As the swing goes up, kinetic energy goes down, and potential energy goes up. But as the swing goes down, kinetic goes up, and potential goes down. But the total energy remains the same over time, which means the answer to this question, the total energy of the swing set as a function of time, is going to be D.